Welcome to this session of the OSCAR-XO2 O&M training. What we strongly suggest is if you have not seen the installation of the OSCAR-XO2 video, we suggest that you do that first. That'll give you a good background or context of what we're going to be talking about here. Once you've done that, we'll just kind of briefly talk about the certification process. We're going to also give you an idea what the OSCAR-XO2 is, some basic inspection procedure checks and so forth, the startup procedures, which is how the electrical works and so forth, and then some basic troubleshooting. So let's get started. The certification process is really pretty simple. You've already started it if you're watching this video now. We either do classroom or mostly online training. Once you've taken a look at the videos, contact us through the email here, and we'll get your name on the certified professional list. And then if there's any additional training you need, whether you need someone to come down on site to go through some things, or you find something you have a question about, you can call, or always at all times you can review this training video as well. So what is an OSCAR-XO2? Well, basically it's a proprietary treatment technology. And as far as the operation and maintenance is concerned, we're just going to break it into two sections to make it real simple. The XO2 refers to basically the treatment units or the treatment tanks. The OSCAR really refers to the final dispersal component. The XO2, the simplest version for a 500 gallon a day system, or let's say a 4-bedroom system, will be two tanks. Each tank is a double compartment, and they're split exactly the same with a 2/3, 1/3 split. The treatment tank will have a bypass hole through the partition wall. It'll either be a hole at 24 inches or so above the top of the floor of the tank, or it could be a T-baffle with the bottom of the baffle about the same height as the flow-through part would be. Pretty much off-the-shelf kind of thing for most precasters. Now this could be, you could find this as a poly tank, concrete tank, or other, whatever's been approved. The discharge tank, the only real difference in that is that we have the same flow-through port that we do with the treatment tank, but on the discharge tank, we want that to be about 12 inches off the bottom of the floor. And this can't be a baffle, it has to be a port in the wall. This is going to allow us to accumulate a certain amount of solids, but yet also have the clarifier allow clear effluent to pass through to where the pump is. Now the OSCAR, or final disposal component, it's just another acronym for an on-site sewage system where we utilize sand in coils of Netafim subsurface drip tubing. And where the sand covers an area of the soil, we call that the recharge area or the disposal area. Now we can break the OSCAR down into two basic parts, the coils and the sand. Other than the plumbing to hook them together, those are the two main components. It's a pretty simple technology. And just to give you an idea of what they look like on the side view, if you're on a flat site, the coil should be somewhere right around the center of the area on the lengthwise. Coils are going to be flat or level. On sloping site, we're going to have the coils more toward the upper end of the basal area. Again, the coils need to be level, so the installer will have put a little bit more sand underneath the downslope side. Other than that, they'll work hydraulically the exact same way. And to give you an idea of what things look like, in the foreground, we got the real lush green grass growth, and it kind of follows along the perimeter on the right, where you can see there's a break between some kind of anemic looking colored grass and the real dark green grass. That's the path of the row of coils, and you can see they're not necessarily in a straight line, but they are in a single line. And then in the background, where you see the yellow arrow placed, there's another OSCAR in the back. You can see the little circles that are head off into the woods. And that's almost a flat side, although it's still sloping. But that gives you an idea what they could look like. Now that you've kind of have an idea of what the OSCAR-XO2 would be, what would be under the ground, we're going to go through a number of the checks that we would be looking at. First, we just want to make some visual observations of what the Oscar looks like. We're going to measure various solids accumulations in the various tanks. We're going to make sure that the aerator is functioning correctly. We're going to go through what we call the startup procedures, which allows us to know, without really having electrical equipment, knowing the wiring, how the system is working. And we're going to use pressures and flows to make those determinations. And then ultimately at the end, we're going to record the observations that we've seen. So looking at some of the visuals, I'm showing these couple of pictures so you can get an idea that the Oscars, depending upon how long they've been in, what climate that they're in, um, you may have some different looks depending upon the circumstances. For instance, in the upper left corner, you can obviously see where the Oscar coils are. You got, circles of lush green grass growth, and yet the grass alongside is dried out. This particular site or picture was taken, late summer, early fall. Hadn't been raining for quite a while. The normal grass had dried out, but because it's being basically dosed with treated effluent around where the coils are, that stays green. This same site, if you were to go back, say in March or April, where it's been raining all winter long, you couldn't tell where the coils are because everything looks pretty much the same. Now the picture to the right is in the springtime in another site where you can tell where the coils are with the green coloring, but it's all within a grass area and everything else is kind of green around it as well. The bottom picture is taken from a fairly new system. It's been in for probably not even a year, in a climate that's extremely hot and dry in the summertime, and very cold, and with some snow in the wintertime. So grass is either going dormant in the wintertime or it's getting dried out real bad in the summer. Over the years, this pattern, this green striping pattern that we see with the coils, they will actually fill in, and it'll be more like the upper left hand picture as opposed to seeing where the individual coil lines are. So anyway, these are all examples of properly functioning Oscar systems, but you can see there's a wide variety of looks that you may see depending upon the area and the time of year. Now here's an Oscar that was put in less than a year ago. It was probably put in either at the late end of the summer, got the sand on top, temperatures got cold, so basically nothing is germinating, or it's only been in for a few weeks. And so it'll just be, just plain sand. In different parts of the country, the sand will have different color depending upon the parent material the sand was taken from. But you'll notice in this case, if you look away from the shadow of the individual taking the picture, you'll see it looks like there's some rivulets of water running out there. Not good. With a little closer inspection, we see these little clam holes. And this would be an indication the Oscar, at least the coils, hydraulically are working the way they're supposed to. The problem is the wrong type of sand was used. It's too fine. It ultimately can take the water, most of it, but instantaneously it can't, so it surfaces. This is easily rectified, but this can happen very, very seldom, but it's usually because of the wrong sand. Here's an Oscar where it's, again, late summer, has had a lot of rain. You can tell the grass in the background is pretty well dried out. This particular Oscar is used pretty heavily, probably 70-80% of its design capacity is used on average every day. You can see you got some really lush, high, tall grass. When you walk up on this, it's solid. And the sand doesn't move. It's going to hold in place with the grass roots real well. So we've got a pretty good idea what the system's supposed to look like, what it is. Now we're going to be looking at some of the treatment tanks. What are the things we should be looking for there? Well, the first thing that I would want to know is what sort of solids accumulations we have in the tanks. In the first compartment, it's just going to be like a septic tank, floating mat with sludge on the bottom. When about 1/3 to 1/2 of the total volume of the tank is filled up with sludge and scum accumulations, it's probably time to pump the tank. The other thing we can look at on the second compartment is when about 40% of the compartment is filled with solids. At that point, we'd want to pump the tank as well. So when we pump one side or the other, we're going to pump them both. We're not just going to try to leave material in one and not the other. We do want to clean both sides at the same time. Now, using standard sludge judge or other measuring devices for finding the sludge and scum layers in the first compartment, I'm going to assume that most everybody's already had an idea how to do that. In the second compartment, it's a little bit different. What we're going to have, if we look inside that aeration chamber, we should see kind of a brownish-looking material here. You can see bubbles are coming up. They're somewhat diffuse, but they'll come to the surface, and then the water's making somewhat of a rolling action. We'll have a little bit of foam or suds on the top. What we'll do there is, while that's on, is we'll just collect a sample of the liquid, and we can put it in really any container. We can put it in a 2-liter Coke bottle. We can put it in here an Inhofe comb or a mason jar. It doesn't matter. But you can see the middle picture. We've just placed that liquid into that Inhofe comb, and stuff settles out pretty quickly, but there's a lot of stuff in suspension that within about 20 minutes, and you see the second picture to the right, that material has settled out. And so we really want that liquid to set for about 20 minutes while we're doing some other checks to indicate how much solids we've accumulated inside their aeration chamber. Here it's hardly any at all. When you look as a percentage, it's probably more like 2 or 3% relative to the amount of liquid volume we have in the tank. Now on the discharge side, we're looking at the large compartment we're going to call the clarifier, and the kind of pump chamber is going to be on the second side where the pump is. But what we're going to do on these tanks is the floats are set at about 22 inches off the bottom of the floor. So we're going to flood the tank at least to that level. And our flow through port's going to be at about 12 inches so that we have the ability in the clarifier to accumulate floating material as well as settled material in the tank. We can get up to about 12 inches on the bottom and a little bit on the top. When the clarifier does get somewhere close to 12 inches accumulation on the bottom, probably time to get that cleaned out. We don't want to carry over a bunch of the solids into the pump chamber side. The pump tank will accumulate solids over time. It will take a long time, but it will accumulate over time. When we get about 8-9 inches of accumulation there is when we want to pump the tank. There really shouldn't be a lot. It should take quite a long time to, while everything is working the way it's supposed to, quite a long time to accumulate things in this tank, but it will, and so we just need to be mindful of that as we move forward. Now once we've got a visual of what the OSCAR looked like. Everything's cool. We've got, the solids measurements or an idea of what we have there. The next thing we need to look at is how's the equipment actually working? Are the valves, the floats, the pumps, aerators, and so forth, are they doing what they're supposed to? And we're going to look at that or know what they're doing, what they're supposed to, depending upon the flows and the pressures that we're able to see during our startup check. Now, to check the floats, they're pretty easy, pretty simple. There's only 2, so you can raise the top float. There's about a 5-second delay in the control panel, so after 5 seconds, we should then hear an alarm sound and the light on the front of the panel should illuminate. The bottom float, we'd have to raise it up, but it might take several minutes for the pump to come on. The cycles are usually about 3 minutes off, about 30 seconds on. So depending upon where the cycle is, we may be standing there with that float held up for quite a long time. The best option that I like to use is what we call check the input screen. And now inside the control panel, we have the capability of being able to diagnose or see what the panel is seeing. So first, I'd like to explain is on the inside door of the panel, we have what I call supplemental wiring diagrams. And I got just an example of a portion of one here on the left where we're showing the bottom float on the right and the top float the bottom float on the left, the top float on the right. And you can see where the leads for each of the pumps land in the terminals, either on 0, 1. On the top float, it's going to be 0, 2. Now this 1 and 2 you'll see they uh, correspond to the input indicators in the control panel. Now, when you look at the Siemens logo, if you don't see the screen where it says, pump cycles and pump runtime, and it says something else, and you're not sure where to go, the easiest thing is just to turn off the circuit breaker for the control power or the main power to the control panel just for a few seconds and turn it back on. And this will be the first screen that will come up. It's an easy one to locate. And then we've got the up and down, left and right arrows on the right. So what we'll do is use the down arrow. We'll go down 3 or 4 spaces to where the date and time is. It doesn't matter if it's correct or flashing. Then we can use the left or the right arrow and go over to the screen that has a large capital I in the upper left corner. That indicates that that's the input screen. Now it's the top row of numbers that we're concerned about. And if you see, the number 1 has a black background, and that 1 corresponds to the same one on the wiring diagram. That's the input indicator for the bottom float in the pump tank. The number 2, it's not backlit, but it also corresponds to the high-level alarm float, which is wired to position number 2. So we don't have to transpose numbers. We can just use 1 for the bottom and 1 and 2 for the top, and it's the same on both screens. 3 is probably the aerator's off, and they're testing that on this particular illustration. So the other thing we can do is, once we look at that input screen and it says, okay, the bottom float is up or it's closed, but it's indicating that the top float is down. If we look inside the pump chamber, we should see the bottom float being lifted by the water, and it should be pointing up. But the top float should be hanging down. We should physically verify, in fact, that's the case. The way this drawing is, some people get confused. They think that there's 4 floats in the tank, and there's actually only 2. They're just, the draftsman showed that as the float can either be up or it can be down. When we're doing a dose, what's actually looking, we'll go into detail what this means, but we're pumping water from a pump inside the tank, goes through our Headworks, out to the OSCAR coils, drips out the coils, and we're good to go. So in order to understand how the controls work, we really need to start with the Headworks. That's kind of where everything is happening. It's kind of the not the brains, but the guts of the head of the unit. What the Headworks has is 3 main components. The first one is we have 5 solenoid valves that we've labeled S1 through S5. We have 3 pressure gauges labeled 1, 2, and 3. One is on the inlet of the pressure to the filter. One is on the downside of the filter, and number 3 is after all the coils. The disc filter is located between gauges 1 and 2. And finally, we have on the very far left is the flow meter. Okay, so we're going to be using all those to tell whether the system is functioning correctly the way it should or not. Thing to remember, the valves that we're using, the solenoid valves, are all normally closed. What that means is the valves need to have power, 24 volts AC, and at least 8 psi in hydraulic pressure in order for them to open. If they don't have both of those, the valve is shut and water won't go through it. So when looking at the control panel, we're going to have 5 toggle switches on the left, and the top one is going to be for our pump. The middle one's going to be for our blower or aerator, and then the bottom 3 are going to be for our valves. Valve 1 and 2 have 1 toggle switch. Valves 3 and 4 have another toggle switch, and valve 5 has its own toggle switch. And then you can see on our bus terminal at the bottom of the picture where we have identified for the floats, valves, pumps, and then our incoming power. And those are all separated by the yellow tabs. It makes it much easier to find and decipher what's going on. You notice that for our floats, we have 0, which is common for both floats, and then number 1 for the bottom of the float, and number 2 for the top float. 3 and 4 are just for an extra alarm if we want to have a remote alarm someplace. Valves with the V's are for the positions for wirings with V's are for our valves. Valves 1 through 3 correspond to uh, valves 1 and 2, valves 3 and 4, valve 5, and then N is going to be a common wire for all those valves. The next thing you see, LP and NP, that's for load for the pump, and it's neutral for the pump. You've got LB and NB, that's going to be load for the blower or neutral for the blower. And then you have the connections for your controls, pump, and blower incoming power. The valves we have a supplemental wire diagram in the panel like this that basically shows the solenoids S1 through S5, and then the terminal connections in the control panel V1, V2, V3, and VN. Each of the solenoids has 2 leads to it. One lead from each solenoid is tied together, and then that one is terminated at position VN inside the control panel. Solenoids 1 and 2, that their second leads are tied together, and those terminate at V1. For solenoids 3 and 4, they tie together, go to V2, and V5 just has the single wire, which will go to V3. So if we want to simulate a dose going to the OSCAR, we can use these toggle switches. The first thing we do is we turn all of the toggle switches to the off position. That way the control panel's not making things happen, only we are. Then what we'll do is we'll turn the valves 1 and 2 toggle switch to hand, and then and that'll give electrical impulse to the solenoids. And then we'll turn pump on the top to hand. That'll give us our hydraulic flow to the valves. And what that'll look like, here's our flow path. We're going to have solenoids S1 and S2, they're energized. Pump is on, and so the flow now will go through the headworks in this fashion. Valves 3, 4, and 5 are closed, so it's like they don't even exist. They're just a blockage. So the flow has to go through S1, go through our flow meter, go through solenoid 2 or valve 2, and then out our flow meter, out the supply line to the coils. That gives us our dose. Then we can verify that that's acting correctly. First of all, this is what it would look like. We've seen this picture before. But in the Headworks, we are going to be able to recognize these pressures on all 3 gauges, gauges 1, 2, and 3. It'll be about 50 psi. They may vary depending upon the pump and various other factors, but give or take, the max it's ever going to see is 52 psi with the pump that we use. You're never going to see much less than maybe 45 psi, but you're really going to see pretty much all the same value. Gauge 3 may be a little less than gauge 1 and 2, but again, it's going to be real close. Now our flow, depending upon the coils and the number of coils that we have, each OS50 coil will allow, at full pressurization, about 0.35 gallons a minute per coil into the sand. Now an OS100 or the larger coils are going to allow twice that at 0.7 gallons a minute once we get pressurized. Now if we want to figure the flow out with our flow meter, we got to understand a little bit of how the flow meter works. First of all, looking at what I call the odometer, it always has 2 black round numbers and then 1 number painted on the side. And the first number here is 2, that's black. It's not 0.2, it's 200. The second position, which is another 2, it's actually worth 20 or 20 gallons. And then when we want to look at the single digits or the 1 gallon, here we have a 0 painted on the face. We have to look at the gauge or the dial on the right. You'll see that dial is identified as X1. It means each digit around that dial is worth 1 gallon. If you look at the center dial, you can barely see it within that little window, but it's at 0.1. Each digit is 1/10 of a gallon. And on the far left, each digit is 1/100th of a gallon. So what's interesting is, for the most part, when we're looking at hydraulics, we're not too concerned about what the actual odometer is. We're really going to be concerned about what that middle dial does, because each rotation is a full gallon. So all we need to do is just time a minute and count the rotations there to know how many gallons a minute flow we have. So let's pretend we've got a system that has 10 OS50 coils. So in other words, our flow should be 3.5 times 10, or about 3.5 gallons a minute. If we have OS100s, then you can do the math there. But this is about the only real math that needs to be done in order to do the operation check on this system. What we need to do first, though, is we turn pumps on, or excuse the pump on with valves 1 and 2, but we need to let the pressure stabilize. Once they're stabilized, then we can time how much flow we have going through there. If we start timing as soon as the pump comes on, the problem is that we're going to be filling a pipe up, and we're really not measuring flow out the emitter. We're just, having, void pipe that we're filling. So what that looks like, when the pump first comes on, you'll see that the dials actually start to turn quite rapidly. And then at the point where the system is fully pressurized, things slow down, and they slow to the rate at which water can now leave the emitters. These are all pressure compensating emitters, so once they get to pressure, they only allow a certain level out, and that's it. And you see this will climb up to about 9/10 of a gallon on that middle dial, and it'll stop. So if we were timing this, we would have timed for a minute. Like I say, just count the rotations. But you'll notice there is another dial. It's called a leak detector in the middle, and it turns very easily with hardly any water going through. But the key here is if sometimes the systems are set up to drain out, especially in colder climates. Once we watch the pump turn off on its own, if the dials start to turn backwards, which they can, we have to know how much they turn backwards to know how much water is running back in the tanks. So we'll have to keep track of how many rotations that we had going out and how many reverse rotations we had coming back to know what our net amount of water that actually got dosed out to the field. And we'll need to record that. The next thing we want to do is we have a filter flush. What will happen with our disc filters, the way they're set up, is the flow of water will come from the left. It'll come into the housing of the filter. It will then go through the outside of the disc filter into the inside of the cartridge, then through the center out to the emitters. That's the normal forward flush, so we get the cleanest quality of effluent going out to the emitters, then into the OSCAR. In order to make this work on a long-term basis, we automatically backflush the system. So we're going to reverse the flow, going from the left to the right to the left. Water will be coming to the inside of the disc filter, somewhat expanding the disc filters apart a little bit and blasting a large volume of water through there to clean that out. And so what we're going to do to simulate that is we will then turn all the toggle switches to off. We will then turn valves 3 and 4 toggle switch to hand, and then turn the pump to hand. And what that'll look like in our Headworks is we'll still come into the same influent T, but instead of going through S1, we're going to go through S3. It'll go backwards through the disc filter, and then all the water will go through solenoid 4, and then back to the tank. And what that looks like is very simple this. So water's just going to get pumped out of the tank, and it's just coming right back in the tank. And this will come at a very high rate. So if we were to watch or observe the water coming in the tank, it'll just about fill up that 4-inch inlet. It'll be about 25 to 28 gallons a minute of water flowing through there. So it's a very high rate. So we're doing a really good job of cleaning out that disc filter. Now we'll be able to identify through our pressure gauges and flow meter if it's working correctly or how correctly it is. What we'll see with our pressure gauges, we'll only be looking at pressures on 2 of them, gauges 1 and 2. Because we're going backwards, gauge 2 is going to get the water and pressure first, so it's going to be about 20 psi. Gauge 1 is going to be about 10 psi, and because we have no water going through or by gauge 3, it's going to be 0. Now, it's not so much the actual number of these pressures, it's going to be the relationship. You see gauge 2 is about twice of what gauge 1 is. Sometimes you'll see 15 and 8. 18 and 9, something like that. But it's very rarely ever it's over 20. But it could be lower than that. But as long as you have that 2-to-1 ratio between gauge 2 and 1, 0 going through 3, you're good to go. And you'll be registering no flow on the flow meter because we don't go through it when we do this particular function. Now, the next sequence is the coil flush. Now that we've got the disc filter clean, then we want to actually clean the coils out. Again, we're going to turn all the toggles to off, and then we'll turn on valve 5 to hand. We'll turn valves 1 and 2 to hand, and the pump to hand. It's going to be similar as we were dosing. The same flow path as we were dosing happens again. We're going to go through solenoid 1, go through the disc filter, through solenoid 2, out the flow meter, out to the coils. But now, because valve 5 is open, all that excess pressure and flow is able to go through and back into the tanks. So what we'll see then, the flow path will look like so. And if we were to observe the water coming into the inlet of the tank, we would probably see about half of the flow that we saw when we were doing just the disc filter. We've got friction loss going in and out to all the coils. We got some pressure and some flow loss in the coils. So we would expect to see less flow coming into the tank. Now our pressures are going to be a little bit different too. Because we're going with the right direction, we're going to see about the same pressure in gauges 1 and 2, roughly about 40 psi. Sometimes we'll see down as low as 35. Sometimes they may be in the low 40s. But again, they're going to be just about the same on gauge 1 and 2. Gauge 3 typically will have no pressure recorded. You might see the needle bouncing a little bit. I've seen pressures up to not quite 4 or 5, but that's very rare. So we're going to see somewhere in those ballparks, the 40-ish to 0, depending on whether we're looking at gauge 1, 2, or 3. And the flow on the meter should be a greater than 12 gallons a minute. And that's, that would be considered normal on a single-family resident application. If we get numbers much different than on the dose, on the filter flush, and then on the coil flush, if we get numbers much different, that means there's probably something askew, something's not working correctly. Give a call, send an email, we can walk you through that. So what's really been happening here on the normal automatic sequence, valve function 1, we call it, which is the dose, it's set for 3 minutes off, 30 seconds on. That will do that 90 times, and we'll repeat that. Then that'll get us about 6 hours, roughly. Once we go through the 90 doses of our doses, the next sequence will get 1 dose of the disc filter back flush. It'll be 30 seconds on, then it'll come on for 15 seconds, clean out that disc filter, and then it'll be off. It only does that 1 time. And then it'll go to valve function 3, which is off for about 30 seconds, and then on for 2 minutes. We're going to flush those coils long enough so that we can get any debris that's there out and have it on for long enough where any debris will then actually flush back into the tank, and it'll be there so that when the pump shuts off, we don't get any drain back to where we don't want it. After that coil flush, we go back to our 90 V1 or dose counts or dose volumes, and we just repeat those 3 valve functions over again: valve 1, 2, and 3. That's what it is, 24/7. As long as there's water available to close that input number 1 or raise the bottom float, we will go through these sequences until that float drops. Now we've completed the startup. We've checked all the floats. We know those are what they're doing. We know the pump works. The solenoid valves are doing what they're supposed to. We've verified that with the pressures and flows. We've recorded those. And now what we want to do is we want to leave all the toggle switches to be in the auto position or up. The circuit breakers are up. The toggle switches are up. If we do nothing else, if we remember that, at least the system will be on or what it's supposed to be when we leave. Now, the one thing that we haven't looked at yet is our aerator. And there's a couple of things that we need to look at when it comes to the aerator. When we show on our illustrations the aerator, we're showing it on top of the tank. Typically, that's not where it's going to be installed. The aerator box that the aerator is in, we want the bottom of that box at an elevation at least as high as the top of the riser going to the tank. What we're trying to avoid is if for some reason we have our tanks get flooded for some reason, power outage, whatever the case may be, we're not going to get a bunch of water into our aerator that would destroy it. Our solenoid valves, our floats, our pumps, they're all made for water. In the flow meter, they can be submerged for a period of time, and they won't hurt them a bit. So I'm not too concerned about their relative elevation as far as that goes. But the aerator, I am. So we'll probably see the aerator around to the side of the house where there's no, a door coming in and out, no place for the family to congregate, and it's something that's somewhat secluded. Or it may be further out in the yard where it's under around trees or bushes or rocks or something where it's not so obvious to see. But if you want to do maintenance on it, you need to know where to look. One of the things that we look at is the aerator functioning? And so for that, it's the easiest thing to do is just to open the lid to the aeration chamber, and this is what we should see. The liquid should be somewhat brownish, an earth tone. We should see the air coming up, not in just one spot, big bubbles, but diffuse out over a whole bunch. So it's coming up along the partition of the tank. It'll then move toward the outlet and then down again. So it's got this rotational motion. The odors, musty smell, definitely smell like we're in a septic tank, but it shouldn't be putrid. It shouldn't knock us down when everything's working normally. So anyway, that's the first indicator. Yes, the aerator is working and we're good. The second thing is to actually look at the aerator itself. Now it's going to be within a box that looks like the picture on the left. It's going to have our low ridge lid and insignia on the top. The box will probably be black. And again, like I say, it may be tucked around the side of the house or off in a bush or something. So look for something that looks like that. Inside the box, you will find the aerator. It's a green lid with kind of a blue turquoise bottom. You'll be a splice box in there for our power cord coming in and out. And you'll notice down at the bottom of the box, there's a 2-inch pipe. That's our air inlet, our air intake. That's where the aerator is going to draw its air from. Looking at the other side of the box, we have the air intake is going to have a couple of 90s. This way, if it rains, water can't get into it. It'll just drop off, but we'll just be able to pull air in no matter what. Now, there is an air filter inside. It's a very coarse air filter. One little screw comes off the top. It's either Phillips or flat screwdriver. The top just lifts off, the green top. And under there is this tan-looking, when it's new anyway, filter. That may catch, the earwigs and sticks and bits of dirt and so forth. I would shake that out or just replace it altogether. Might be the best way. They're fairly inexpensive, and they're not secured in there in any way. You can just pull them out, pop another one in, put the lid back on, put the screw in, and you're done. Now, the last thing we need to do with the aerator is test the alarm. And we use a pressure sensor, we use a current sensor to indicate whether we've got an aerator failure or not. So if we have all of our toggle switches are in the up position, we have our circuit breakers on the right, all up and everything's working, everything is fine. So if we take the circuit breaker for the blower or aerator and turn it off, when everything else is left on, we turn it off. What will happen is the controller will sense that we no longer have any power or current going to the aerator, and it'll sound an alarm. Once we know that the alarm sounds, we know the current sensor's still working, we know that the aerator's been working, so we can turn the blower back on and we're good to go. So now that we've done all the checks, we've done the visuals, we've measured the solids accumulations, we've got the hydraulics test for all the valves and pumps and so forth done, we've serviced the aerator, we really need to well record those things. Those are the kinds of areas of information that we want to have down. Now, each local health jurisdiction or state jurisdiction may have different requirements that they want written down. But these 5 areas are going to be recorded to write down. We may have to write the pressures during not only the cycle, but the backflush cycles. They may want to do the flow rates during the dose as well as the backflush or the flush. And then on the solids accumulations, we'll have to break that down, obviously, between the 2 chambers and the 2 tanks, and then indicate maybe when it's going to need to be pumped and so forth, and then what's going on with the aerator. Well, once you get to that point, you've done your first check. Again, if there's any other questions that you have, please feel free to contact us. Happy to answer those questions. Send an email. This comes directly to our inbox. At that point, we'll be able to have a conversation. We're really good at returning calls, and maybe later that day or at the worst the next day, but we get back pretty quick. Thank you for watching, and hope you enjoy. Thank you.